we start with questions? Is there something that you'd like to ask about?
Not this week. I started looking at Professor Finley's website and applying what we learned, so next week I'll probably have a couple of questions. But.
Okay. All right. So let me pick up where we stopped last time, and we'll be basically talking about, let's see, we're basically talking about cosmology. So let me give you a review of cosmology. It's almost something that you can just read in a book, so I don't know. I mean, there aren't many equations. Basically, astronomical observations tell us that the universe is, observationally at least, flat on large scales. And the CMB is uniform to about 1 part in 10 to the 5th, the cosmic microwave background radiation, that is. These and other facts and observations and ideas suggest that potential energy expanded the universe very rapidly right before the Big Bang, that there was an expansion called inflation, and so there was an era of inflation. I'm going to try this liquid chalk. I don't know if it'll work. In any event, we had an era of inflation, but this was very brief, possibly some people even say 10 to the minus 35 seconds, which is absurdly brief. It could well have been longer than that. In any event, the idea is that the universe expanded by something like e to the 60, which is roughly 10 to the 26. And what happened was that it was potential energy. The idea is that potential energy caused this remarkable expansion. And one picture, which is called chaotic inflation and was put forward by Andre Linde, if I have his name correctly, is that that you had a prior universe, and at some point in the prior universe, a scalar field just underwent a quantum fluctuation to a very high value. And so the potential energy of that quantum field, if you just think of it as a free scalar field, it's this curve here is 1/2 m phi squared. If it somehow fluctuated from phi equals 0, so this is v equal to that. So this is sort of a long function. And this is phi. This is the phi axis. If the thing somehow fluctuated from its mean value, its vacuum value to some place here, then with a suitable value for m, you would have had in the vicinity of that fluctuation an enormously high potential energy. There's also an effect due to general relativity, which I should have included in the book, and maybe I will. And it's basically called gravitational friction, or you can think of it as gravitational friction. Once there is a big fluctuation, it's hard to get back down. I mean, it comes back down, of course. There's enormous restoring force, but because of gravity, there's a viscous force, or like an air resistance to the gravity. So it takes a while to get down. And so in this period, which might be 10 to the minus 35 seconds, might be 10 to the minus 20 seconds, 10 to the minus 9 seconds, I don't know. Anyway, during that time, there was an enormous expansion because of that energy density. In a little while, we'll see the equations that govern that. Anyway, that's the very beginning. And then this potential energy then turned into radiation, and the radiation was the Big Bang. And of course, the Big Bang happened almost immediately after inflation, within, say, a nanosecond. Also, because this thing expanded so rapidly, if you had a tiny region where the fluctuation occurred within a nanosecond or whatever, it was 10 to the 26 times bigger in radius. And so there's just an enormous amount of energy available. You might wonder, what about conservation of energy? Well, gravitational potential energy often is negative, and the gravitational potential energy compensates for this enormous increase in positive potential energy. And then, boom, that turns into radiation. And so then we had an era of radiation. And this lasted of the order of 50,000 years. Let us say, the year of radiation was about 50,000 years. By that I mean that most of the energy was radiation for about 50,000 years. On the other hand, the momentum of a particle falls as the universe expands, whereas the mass of a particle doesn't. The era of radiation gave way to an era of matter. And so the next was an era of matter. And then eventually we had an era of dark energy. And so this was a sequence. Let me give you the times here. And in fact, inside this era of matter, at about 380,000 years, the universe became rapidly transparent. So until 380,000, it was a plasma of electrons, photons, and then dark matter, which I haven't talked about yet very much. Nobody can say very much because we don't know what the hell it is. But anyway, there was photons would be scattered. Mean free path of photons was, I don't know, I'm just guessing off the top of my head. It might have been a micron, it might have been a nanometer, it might have been possibly even a meter, but even so. Actually, I very much doubt that it was anywhere near a meter. Let's stay down in the micron range. This point here is where we got KT to be 0.26 eV. So that's when the universe became transparent. And at that point, only 1% of atoms were ionized. And so the universe then became transparent, and it's basically been transparent ever since. And the photons that last scattered here were the CMB radiation. This transition from an era of radiation to an era of matter, this occurred when KT was about 0.81 eV. So that's when the energy density shifted from radiation to matter. Okay. The era of dark energy started about 3.5 billion years ago, and we're currently at a time of 13.817 billion years. That's the present estimate of the age of the universe. If we subtract 3.5, what we get is about 10.3. So the transition from an era of matter to an era of dark energy was about 10.3 billion years, giga-years, as the Europeans would say, after the Big Bang. And now we're in this age of dark energy. We don't know what dark energy is. It's probably potential energy. Whether that potential energy is related to the potential energy of inflation, I don't know. Nobody knows. Some people even think that dark energy is an astronomical mistake, but it's been pretty consistent with everything else for a decade or so now. So it's I don't know if it's, we call it settled physics, but it's reasonably well established. Anyway, the dark energy density is something like 5.8. Let me just say 5.8 times 10 to the minus 30, and this is c squared grams per centimeter cubed. So c squared grams giving you energy, mass times c squared. And this is now about 68.5% of the energy density of the universe. The critical energy density is, we'll get to this mathematically later, it's 3h0 squared over 8 pi g. Astronomers, you know, they do everything backwards. I mean, we think of t0 as time zero, the initial point when things started. No, astronomers use 0 for now. I don't know, are you no, okay. I mean, they just drive me nuts. Anyway, so this is the critical energy density, and this is about 1.88 times 10 to the minus 29. Again, c squared g per centimeter cubed. Or effectively 18 parts 10 to the minus 30. Okay, there's something a little screwy here then, because 5.8 is not 68% of 18. So it may be that one of these numbers is old, and so I better check that. Anyway, what is H0? H0 is the Hubble Constant, and people write it as 100 H kilometers per second per, and then astronomers use this term megaparsec, which is about 3 million light years. Why they can't just use light years, I don't know. Why they use Planck's constant for little h, I don't know. I'm switching to a notation, which I'm putting a 0 on that, since in any event, it's h at this time, to use the astronomical convention. Okay, matter, if this is dark energy, matter is, well, it's obviously what's left. 38% is matter. Now, of this matter, most of it is dark, and basically 15% of the matter is the matter we know about. 85% is the matter we don't know, and it's called dark matter. There have been attempts to detect it, and they've all failed so far. And this is one of the huge mysteries of modern physics, and presumably will be discovered, detected. It's in a sense already discovered, because you can see that the orbits of stars around galaxies and galaxies around the centers of clusters of galaxies are such that the stars and the galaxies are moving faster than they would if only if the gravity that's holding them in those orbits were only that of the stars that we can see. And of course, there's that bullet cluster picture. You remember that? Yeah. So in a sense, it's been observed, but it hasn't been detected. And when it is, if it is, that'll be an enormous change in physics, and as big a change, I think, as the discovery of the Higgs, maybe even more so. I mean, the Higgs was predicted, and when it was found, it was, so there it is. It's where we thought it was. If dark matter is found, it'll be a big surprise, because nobody knows what it is. Okay. So Einstein's equations, as you know, are they're formally 16 second-order nonlinear partial differential equations, but because of the symmetry GJI equals GIJ, there are only 10, and there are 10 then partial differential equations in terms of 10 components of the stress energy tensor, because we don't know what the stress energy tensor is either. And the equations, as I said, are terribly nonlinear. And so the thing is, it's enough to throw one into despair, drive one to drink. But remarkably enough, some physicists using the spherical cow approximation made a lot of progress, and these are basically Friedman-Walker and Robinson, I think. Yeah, Friedman-Robertson-Walker. Made certain assumptions, and the assumptions are that space, or that the energy momentum distribution in space is homogeneous, which is a fancy word for uniform, and also isotropic. And but this is in space. In space, it's that way. Time is different, but things evolve in time. So it turns out, if you say the universe is homogeneous and isotropic, you can show, I'm not going to show it, but you can show, Carroll gives a description in his book, that the metric then is ds squared. Am I writing too small? What do you think? Do you think it's visible?
Yeah, I think so.
All right. The ds squared then is minus c squared dt squared plus a squared, and let me write it explicitly as a squared of t times dr squared over 1 minus k r squared plus r squared, and I'll write this just as d omega squared because I'm running out of room there. D omega squared is just a normal measure on a sphere, which is d theta squared plus sine squared theta dt squared. So in other words, it's I mean, you couldn't ask for anything nicer. You know, it's just an ordinary time, not changed at all. Again, these coordinates, because what we're doing here is we're taking advantage of general relativity's ability to be written in terms of arbitrary coordinates, so we can choose nice coordinates. And these nice coordinates, ds squared is minus c squared dt squared plus a scale factor squared, that's a squared, and then this form. And here we've got this k, which is it's 0 if the universe is perfectly flat. It's 1 if the universe is, if the spatial universe is basically, if space, three-dimensional space, is actually the surface of a sphere in 4 dimensions. And then it's -1 if three-dimensional space has negative curvature, so it's the opposite of a sphere, and it's some sort of a hyperbolic space, unbounded. In the case of k equals 1, the universe is, the spatial universe is finite. So it turns out that one can, there's something quite cute that can be done, namely you can embed the, as you know, you can always embed a manifold in Euclidean space of a suitably high dimension. And then once it's in that Euclidean space Rn, whatever n is, you can then impose a metric, either the Minkowski metric or a Euclidean metric or some other metric. It turns out that the choice k, of course, if k is 0, what we're talking about is flat space, and so the only thing is this a squared, and so three-dimensional space is just infinite flat three-dimensional space, and we don't need to talk about it things very much. GR still applies, though, with regard to a squared, and flat space is the best approximation that we know of, or it's as good as any other. If k equals 1, it turns out we can embed this, it's then this surface of a sphere, it's called this S3, which is the surface of a sphere in 4 dimensions. We can embed that, of course, in a space of 4 dimensions, and so we need altogether an embedding space of 5 dimensions. Let me see if I can. Hey, guys, could you quiet down a little bit? So, in the case of an open hyperbolic universe, with k equals -1, you can get away with 5 dimensions, a 5-dimensional embedding space, if you give that, choose that the instead of a Minkowski metric, which would be -1 plus 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 plus, you have a -1 plus 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 minus. Then you can get away with 5 dimensions. Whether you can get away with an ordinary Minkowski metric, but more in more dimensions, I don't know. I imagine you can, but I haven't seen a discussion. Anyway, the points P, I can maybe get away with writing them here. The points P for for k plus 1 are T, A sine chi, sine theta, cos phi, A sine chi, sine theta, sine phi, A sine chi, cos theta, and then the last one is just A cosine chi. So this is very much like spherical coordinates in 4 dimensions. In 3 dimensions, it's just upscale 1. And for the case of k equals 0, of course, you just write it as a 4 vector, and then it's just T, A, and then R sine theta cosine phi, R sine theta sine phi, and then R cosine phi. Cosine theta, sorry. And then for the hyperbolic case, what you do is you just put in an H here. So you make these guys cinches and pashas. And then in all 3 cases, then you get this metric, which is called the Friedman-Robertson-Walker metric. And this is a metric in which Gij then is -1 a squared over 1 minus kr squared, and then a squared r squared, a squared r squared sine squared theta. And everything else is 0, and it's diagonal. Okay, so once we have this, we can now calculate the Christoffel symbols. And in particular, let's just, I don't know if I should do them all explicitly, but we can say that this one is a half, just using our formula for the Christoffel symbols, which are the inverse metric tensor and then times 3 terms involving the derivatives. It's G LK comma L plus G LK comma L. I'm puzzled that we have them twice there. GLL comma K. I suppose what happens is that this is KL and I just took advantage of the symmetry. In any event, the K, of course, can only be 0 because this metric is diagonal, and so its inverse is diagonal. And so this is actually just a half G00. And now we have GL0 comma L plus GL0 comma L minus GLL comma 0. And these guys are off diagonal, and so they're 0 because the metric is diagonal. And so this thing is just 1/2 GLL comma 0. Also, this guy is just -1, and that cancels the minus sign here. So that gives us that one. If we compute all right, the implications of that are that G0011 is just a half G11, which is this thing, time derivative, and R, of course, is, we're not thinking of R as time dependent. In fact, we're thinking, in fact, R is one of the coordinates. So it's, that A is time derivative. So this is 2A dot over 1 minus K R squared. So that's gamma 0, 1, 1. Similarly, gamma 0, 2, 2 is A dot R squared, and then gamma 0, 3, 3 is A dot R squared, and then sine squared theta. So those are pretty easy to compute. The other gamma 0 ij's all vanish. On the other hand, gamma L, 0L. Well, this one, it's a similar formula, but let me just skip the initial steps. What you get is GLL times GLL comma 0. And so what you get then is you just get 2A dot, and then the 2 gets canceled, and then this cancels something, and so all of these are just nothing more than A dot over A, which in fact is what we call the Hubble constant. And then you can also, in similar ways, compute the other gammas. And what you always do is you just use the formula analogous to this to compute the others. And so then, let me just mention one of them, for example. Gamma 3, 2, 3 is cotangent theta. And so then we can use our formulas for the curvature tensor, and in particular we're interested in the trace of the curvature tensor. So what we have, one of them, for example, is R00, and so this is Rn 0, N0, and so I think of this as D0 plus gamma 0 commutated dn plus gamma n, and it's the n0 component of that. And what we can find is that gamma 0, gamma n, that commutator n0 is in fact 3 A dot over A. Gee, where are we? I may be running out of ink. Also, the time derivative of gamma n, n0 is 3 times the time derivative of A dot over A, and that turns out to be 3 A double dot over A minus 3 A dot over A squared. So this is starting to become faint, isn't it?
A little bit, yeah.
You think I should switch to chalk?
That might be better. I haven't zoomed in a little bit.
All right. So, the situation is we'll be using 2 or 3 of these per lecture, and I think that's going to exceed the university's budget by a considerable margin. Anyway, when all is said and done, this R00 is equal to 3 A A double dot over A. And in a similar way, in other words, we have to compute all the, well, in fact, we have computed all the Christoffel symbols. I mean, I skipped the computation, but in a similar way, one can compute the other components here, and in particular, R11 is minus something I'll call A over 1 minus K R squared, and then R22 is minus R squared A, and then R33 is minus R squared A sine squared theta. Okay, and you can see that this pattern here is the pattern that we see in the diagonal part of the matrix, metric tensor. And now, what is this mysterious A? This A is equal to a double dot plus 2 a dot squared plus 2k. And so we can compute the scalar curvature then, and the scalar curvature R, which of course is just a trace of Rij. This R, in other words, it's GAB, RAB, and we can compute that, and it turns out to be minus 6 over A squared times a double dot plus a dot squared plus K. And so we've lost one of those terms. Now, I should have mentioned that the Robertson-Walker coordinates are co-moving coordinates, or we're going to assume that they're co-moving coordinates. And by co-moving, what we mean is that the energy momentum tensor, which is Tij, which in general is P Gij, plus rho plus P, rho the energy density, P the pressure, Ui, Uj. This takes a simpler form because in co-moving coordinates, U sub I is just 1, 0, 0, 0. Because we're flowing with the flow, basically. And so in this case, Tij has a somewhat simple form, namely it's a rho here, and then we have P G11, P G22, P G33. And so that's a nice form. The trace, which is T, which we write as T, which is Gij, Tij, this then is, well, it's just this trace. So it's minus rho, that's the first term, and then because we're multiplying by the inverse of the metric tensor, we just get P 3 times. So plus 3 times P. And this is an important combination, rho plus Well, it's actually rho plus 3p that's the important combination. This one is minus rho plus 3p. But anyway, we can now then put this into Einstein's equation and get something very interesting and very important. Let me write down the Einstein equation that we'll be using. I should have repeated it here in the 7, 8. Okay, the particular Einstein equation that I want to use here is Rij is equal to minus 8 pi g over c to the 4 times Tij minus t over 2 Gij. And so if we substitute that in there, what happens is we get, and of course we have to use what, we're going to use the 0, 0 component of this. The 0, 0 component is 3a double dot over a. And so when we do all that, what we get is we get this equation, a double dot over a is equal to minus 4 pi g over 3. And then we get rho plus 3p. And so this is the quantity that I said that I mistook the other one for. This is the thing that's really important because it tells us whether or not the universe is accelerating. Or, no, it doesn't tell us whether or not. It tells us how it's accelerating. So, for example, a double dot over a is always non-zero as long as rho plus 3p is non-zero. So the universe, the scale factor is accelerating. But when rho plus 3p is negative, the minus signs cancel, and the acceleration of the scale factor is positive, and so you get an acceleration of the expansion. On the other hand, when rho plus 3p is positive, the minus sign takes over, and the acceleration slows down. It's decelerating. And in the old days, one didn't think much of this term. And so one assumed this was always positive. And in that case, what you had was a universe that the picture was that you had a big bang, the universe expanded and then contracted. And so people were wondering, well, where are we? Are we in the phase where it's expanding, or are we in the phase where it's contracting? And of course, observationally, the universe is flat, and so the astronomers could never tell us. I'm speaking of maybe 50 years ago, when, well, even 30 years ago, before dark energy was discovered. Okay, so this was from the 0, 0 Einstein equation. So these are the Einstein equations. The 0, 0 give us that. The Ij equations, well, you'd think they'd give us 3 different equations, but because of the isotropy, we don't get 3, we only get 1. And the extra equation that we get is a double dot over a plus 2 a dot over a squared plus 2 k over a squared is 4 pi big G rho minus G. Now that's not G as a function of rho minus G, G time. So this is the other equation. And what you can do is you can use this equation to eliminate the second derivative here. In other words, you could just take a double dot over a equal to this and substitute in there. And then you get another equation, which is a dot over a squared is equal to 8 times g over 3 times the energy density minus k, which is 0 or plus or minus 1 over the square of the scale factor. Okay, so basically these are known as the Friedmann equations. And the two that are most useful now are the two that are simplest, namely this one and this one. So we basically have two equations. Einstein's equations give us these two, but it's simpler to use these two to make a third, and then to use the first one and the third one. And these are normally called the Friedmann equations. And so you see we've gone, there's been an enormous simplification here. Instead of having 16 nonlinear partial differential equations in terms of the Tij, we now have just two equations in terms of rho and p, and these two equations are just equations for the scale factor, how much space is expanding, and of course they are nonlinear equations because rho varies with time according to the scale factor. Now this A dot over A, of course, is what I said was, this is the Hubble constant is A dot over A, and you can see this is an inverse time. And anytime you have inverses or negatives, you're just asking for trouble. But somehow the astronomers love trouble. And so they're always defining things in terms of complicated things like inverses. I think it'd be much better to have something that would be A over A dot, and that would be called the Hubble time. Inverse time is just a stupid way to do physics. Anyway, one of Friedmann's equations, the first order equation, this one, notice this is first order in time, this one's second order. The first order in time one then is h squared is 8 pi g over 3 rho minus k over a squared. Okay, suppose the universe is totally flat and k equals 0. As I said, observations just can't tell us at this stage what it is. The energy density of a flat universe is what we call the critical energy density. And so we write that as rho critical 3h squared over 8 pi g. So this is what rho would be if k were 0. So this critical, of course, varies with time because it's whatever the Hubble constant. See, these astronomers, this notation is just insane. The Hubble constant is not constant. And moreover, it's defined as an inverse. I mean, I don't know what these people are thinking. Probably they're not thinking. I'm making a lot of enemies. So this is the picture. Now the ratio of rho to rho critical is what people call omega. And And so that's how much the energy density differs from what would make a flat universe. And this is equal to, this omega is equal to 8 pi big G over 3 h squared rho. So this is 1 over rho critical. And if we use a prior equation, namely this equation, we can see that omega, in fact, is equal to 1 plus k over AH squared. Or equivalently, 1 plus k over A dot squared. And so, in a flat universe, obviously k is 0 and omega is exactly 1. On the other hand, as AH goes to infinity, no matter what k is, in fact k is plus or minus 1 or 0, omega also goes to unity. So for physics on a large scale, it's typically true that omega goes to 1. And one effect of inflation is to explain why it is that omega is 1. And the idea here is very simple, namely that if what happened during inflation was that things got expanded enormously rapidly, and that made the universe initially flat because the expansion just flattened everything. When I say flat, I mean the spatial curvature, just simply R, big R, was driven to 0 effectively because of the enormous inflationary expansion. What we know now is that omega is 0, okay, this is now, is 1.000 plus or minus 0.036. And it turns out that this is actually a very unlikely value because in a universe without a lot of potential energy causing inflation or causing, as it does now, or it has for the last 3.5 billion years, caused an acceleration of the expansion of the universe. Without that, we'd expect that omega would deviate from 1 by quite a bit. And the idea here is the following, that you have conservation of, more or less conservation of matter, and that means that A cubed rho m, rho matter is constant. So time derivative 0. So rho matter goes down as 1 over A cubed. On the other hand, radiation energy goes down even faster because it goes as A to the 4th. That is to say, not only do you have the number of photons, the density of photons goes down as 1 over A cubed, but also the wavelengths, their wavelengths increase, and so you have A to the 4th rho has no time derivative. And so what we have then is that rho A to the n which I'm going to call, just to simplify the notation, 3f squared over 8 pi g, n being 3 or 4. Then Friedman's first order equation gives us a dot squared is equal to 8 pi g over 3 rho a squared minus k, and this is f squared over a to the n minus 2 minus k. So that's why I defined f in this screwy way. And notice that for practical purposes, if we're in what we're thinking of here is that we're in an era of, we're thinking of an era of matter or an era of radiation. In either case, we adjust the value of n, and we're thinking most of the energy is matter, most of the energy is radiation. And we're leaving out anything like dark energy. And so what do we find? Well, this is an equation we can integrate. F is a constant, K is a constant, we can integrate this. And what we get is A dot is equal to F, a constant, over A to the n minus 2 over 2. And so that means that A goes as T to the 2 over n. And of course that means also that A dot is more or less T to the 2 over n minus 1. Just differentiating. And so this gives us an omega minus 1, where I'm using this equation up here, this huge, long equation. Omega is 1 plus k over a dot squared. So omega minus 1 is 1 over a dot squared. And so this is something like T to the 2 minus 4 over n. And so what you see is that in fact, since n is 3 or 4, this says that omega minus 1 in an era of matter or an era of energy would just always be increasing. And that means that in order to have this value now, we would have had to have started with omega after the Big Bang to be, let us say, omega at 1 second would have had to be unity to within 6 parts in 10 to the 14. And so the only explanation for how it is that we've got so much flatness now, and of course, now we've only had 3.5 billion years of dark energy, and so it's not that big an effect yet. If we leave out inflation, this is very hard to explain, that the present value is there. And so that's the reason for inflation. And as I said, it was Linde is one of the people who invented it, another one is Goose, and probably others not been so lucky. By the way, this thing here is this is T for radiation and T to the 2/3 of matter. Okay. We're out of time, aren't we? Okay, so we've gotten to a reasonable place here, I think. So why don't we, do you have any questions? Okay, I want to